Great, thanks for having us today. And we really wanted to take the opportunity to just sort of think through what an end-to-end deployment of confidential computing might look like under a use case that combines a whole bunch of different components and needs and regulatory issues as well. So we're going to try to go pretty quickly because we've only got 15 minutes. So we're going to start just with our basic use case. Today is grocery day, and we've got a nice family here. They're gathering their vegetables from the local shopping market. The big problem, though, is that as they go to leave, they realize that it's pouring rain outside. And so, fortunately, we've been making great leaps with autonomous vehicles these days, and so we can just pull out our phones, open the app, and summon a vehicle close to us. But really, we need to dig in a little bit further into what is actually happening behind the scenes. And the question is, how, of course, does the van get to the store to come and pick us up? Well, it all starts with a bunch of fleet data in the bottom right-hand corner. And so we've got, thousands of cars, and they're driving millions of miles a year. We're gathering data about how they drive, and all of that data is regulated, of course, because it contains personal identifying information, contains location information, and so that information can't just be shared publicly. Somehow that data is then is gathered together, and we produce a corpus of data which is used to generate a model. A lot of times this might be done on premise. If you've got a lot of hardware on premise, this could also be done in the cloud. But we've got to take that data and we've got to create some sort of an AI model to actually drive this vehicle. And so once we have our model and all of our other software created, we can actually deploy an instance of this in the cloud. We need to have a coordination and control structure, which is also going to handle a bunch of regulated information. And that will get deployed out to the actual vehicle, in this case, which will have AI models on it, which are proprietary and probably shouldn't be leaked. As well as autonomous safety systems, which we want to definitely keep secure. We don't want rogue actors being able to attack that vehicle. And so finally, when we actually push that summon button on the phone, we have identity and location there, location data there as well. And so, really, this wonderful feature that we all hope to have and at least stay dry when we walk out of the store. That's the ideal goal here. But really, just walking through this is a sort of landmine of regulations and regulated data. And the question is, how can we actually do this? And our hope here is that confidential computing and AI are really just a match made in heaven. And our goal question here, of course, is how do we actually protect this data end to end? So, Mark, I'm going to turn it over to you.
Yep. So, protecting your data end to end, it really comes down to a combination of existing technologies that get enhanced with confidential computing. So you look at this first point here, well understood process, encrypting your data at rest, protecting from others, right? The data that you're storing in these devices in non-volatile memory. Now, of course, adding to this, your second level of encryption has to do with your communication link. So if we can go to the next slide, Nathaniel. Another well-understood construct, right? You establish secure links, you encrypt those links, and then you can transfer your data from one location to another. Now, things get really interesting in the next slide. Now, with the ability to isolate your workloads and protect your data and algorithms while in use with confidential compute, you're not only decoupling your application from the underlying infrastructure, but you're also enabling the ability to stitch your end-to-end system with a new level of security. So the idea here is being able to extend the security that you've established with the encryption of the data at rest, or establishing that secure link, moving that into the realm of confidential compute means that you're establishing these environments, you're establishing these connections, you're encrypting your data, while you're computing in that secure environment. So if you take the journey of data from the car up to the cloud, or from your device to the cloud, what you're doing is you're moving from one trusted execution environment to another trusted execution environment. And even the step to store that data is all done without this data ever being accessible or exposed. And that ability with confidential compute is what creates the end-to-end security, from encrypted data all the way up to delivery and absorption of this data and processing of this data in the various locations. Now, the key to establishing end-to-end security starts with evidence to confirm that the sensitive workloads are landing in the secure environment. This process is referred to as attestation, and it can be broken up into two steps. First, you need to collect data from the supply chain that identifies the device and identifies the firmware. And that process we call endorsement, and you can see that in the bottom left corner of this image. Then you collect the measurements from each device in the field. And finally, you validate the data that you've collected against the endorsement information supplied by the supplier. You apply policy to that step, and together with that information, you're deciding whether the endpoint can be trusted. And that's what enables that secure environment. And only once you've established that secure environment can you really start working in this trusted environment. Nathaniel, I'll pass it back to you now to talk about how you scale this work.
Thanks, Mark. Yeah, so as you've seen, we've seen sort of like the trees, if you were, and now I want to zoom out and I want to take a look at the forest. So it's fairly obvious we want to move from that data at rest, data in transit, now to data in use. And the way that we're going to get assurances about all of this is attestation. What does it actually look like to deploy this whole thing at scale? And to be able to create the sort of dynamic relationships that are necessary in order to deploy this in the cloud. And so essentially, we think the major answer for this is going to be open standards. We really need a set of three standards, but let's actually talk through what this chart is on the right. Really, when you think about confidential computing, I used to think about confidential computing as primarily a privacy technology. But now I think about confidential computing as primarily a supply chain technology. If you go to the store, that grocery store we started with, and you pick up a head of lettuce, and it has some sort of contamination that makes you sick, we can trace that head of lettuce all the way back to the row in the field within which that head of lettuce was grown, and we can correlate it to other issues. But without confidential computing, we really don't have any sort of equivalence to that in the computing space. And so, really, what we're dealing with when we actually deploy a computation is we're actually dealing with the instantiation of three different supply chains. So, if you look on the right hand side, you'll see our three different colored supply chains there, and those are hardware, firmware, and software. And so I'm not going to zoom in right now on the details of those particular supply chains, but the key point is that each one produces a deployable artifact, whether it's hardware, whether it's firmware that's associated with that hardware, or whether it's some sort of a software workload. And each one of those supply chains produces that deployable artifact, and that deployable artifact needs to be endorsed in some way. That is, we are claiming certain properties about the provenance of that artifact. And then we end up combining those three artifacts into a single instantiation for computation. And that verification, of course, we need to have verification of that instance. And so in this case, we have two nodes on the bottom. Each of those node is one instance of a confidential supply chain, but we need to have verification between the nodes to be able to determine that each of the nodes is running precisely the supply chain that we think that they are running, and that they are doing so in an environment which provides confidentiality and integrity. And so that verification step is where that attestation is occurring, but we need to have a dynamic relationship in that verification so that we can build that next layer up, which is the mutually attested TLS. And that mutually attested TLS is precisely the thing that will allow us to communicate between the nodes and have assurances about the supply chain on both sides. So it's actually ends up tightening both not only the data in use, but also the data in transit as well. And so if we zoom in on each of these points, the first one is endorsement, right? And this is really all about how we establish trust in a particular supply chain. One of the big things that we have here is that right now, all of our endorsement protocols that exist in the industry are proprietary. They don't, while sometimes they use some open formats, there's no real standard API, nor is there really any standard way to articulate common sets of data within those data formats. And so this is something that impedes more dynamic relationships because we're just relying on vendor specific formats. Another problem that we have is that the way that we primarily think about doing things like attestation today is related to the hashes that identify the deployment artifact for each of those supply chains. But really, that's non-human readable data, and we need to find ways to be able to express this in human readable ways. So this means we need reliable and standard ways to map between names and versions of, say, hardware, software, and firmware, uh, and the hashes that correlate to them. One of the big problems that still remains in the process of being solved, and different parties are solving this in different ways, is the question of who authorizes firmware upgrades. So it's one thing to sort of bring up a trusted confidential VM, and then you can attest that confidential VM. But what happens when you need to upgrade the firmware that's underneath that? Well, we can attest that firmware as part of the attestation process up front, but what happens with live upgrades? Does that happen dynamically? And who authorizes that? And who validates that chain? And who establishes trust in that? So there's not clear industry mechanisms for that yet. And one of the things that's really important about endorsement is this question of static endorsement versus cycle management. So we very often, when we talk about endorsement, we fall into this trap of talking about we want to endorse a thing and that endorsement sort of lives forever. But really, there's a life cycle for all of these deployable artifacts, right? Hardware has a particular cycle, firmware has a particular life cycle, same with software. Both firmware and software, of course, can have CVEs. Vulnerabilities that necessitate upgrades, but you can also have things like physical compromises of hardware. So, for example, if a truck full of CPUs it gets stolen, technically speaking, the system should theoretically still be secure, but wouldn't you want to know that they're in a physically compromised environment? So all of this relates to the question of lifecycle management around these supply chains and how we need to be able to express endorsement not as a one-time fact that exists forever, but as something that is a stream of data updating information about the life cycle of that endorsement. Moving on to verification, this is where we were previously trying to establish trust in a particular supply chain. Now we're trying to establish trust in a particular compute instance as an instance of a set of supply chains. And here again, we have a variety of sort of proprietary approaches, but what we really need to be able to enable more dynamic relationships between these components is a set of standard APIs and formats. One such open source project is the Raisin project, which is sponsored by ARM. It is completely open source and is a member project of the Confidential Computing Consortium. So go check that out if you're interested. But we really want to find a way to enable this to be more broadly adopted in a way that's again standardized, so that we can have more dynamic relationships. There's also the question of version policy interpretation. And basically, the way a lot of us are sort of thinking about verification right now is I want to state a broad set of human readable statements about policy, but then I'll allow somebody to sort of interpret that policy. So if I were to say, for example, I want to take a particular I want to trust an ARM CPU, manufactured by Samsung. Let's pick a random case here. um, should all Samsung CPUs be included in that? And how do I version which particular possible resolutions of that policy are enabled, and at what time they are enabled? So we basically need to be able to fully articulate a policy that has no ambiguity left to resolve or interpret. And you can sort of think of this like if you're a Rust programmer, like the cargo lock file, where you would specify a dependency and say, I need dependency A, version one or later. But then we actually resolve down to a particular version and we lock that into place so that we can track the precise supply chain over time. So we need something like this as well for verification. Finally, we need to make sure that we extend this into device attach. So as we're attaching individual devices, things like GPUs and other accelerators, how do we extend this same sort of model over that? Because we end up with multiple sets of hardware, firmware, and software supply chains within a single instance. So that needs to be considered as well. The third step is building mutually attested TLS. And this is for really establishing trusted communications. And we have some standards in this. There's good work going forward, thanks to Thomas Fasadi for driving this. And but really, this depends upon that set of standard APIs for verification, as well as standard APIs for endorsement as well. That's what's going to really be able to build this up to the scale at which we need a deployment, right? If you want to talk about it at web scale, that's precisely what we're talking about here. And so really this is the sort of big picture end-to-end privacy vision that we want to be able to build at ARM. And we can do this, today. We've announced, of course, RME support in the Neoverse V3 product. There's an announcement today about the automotive product as well. So you'll be able to do those on ARMs in the near future. So, but yeah, that's really the end-to-end vision that we want to see, that data in rest, data in transit, data in use, all over the whole ecosystem with really wide scalabilities and a nice, strong privacy model for the full end-to-end connection of that data. And really, that's our talk.